two announcements. First one is about the homework 4, which is due, or about the things that are not in homework 4. So homework 4 is due Monday, right? But I told you that I'm going to give you the source panel problem that was part of homework 3 and homework 4, but I have not included that in homework 4. So whoever submits the source panel theory from source panel problem from homework 3 will get 2 bonus points. So 1% of the grade. And it is going to be due the same day. So 2 bonus points. I think there are 2 students who have already submitted this and have received their bonuses. Yes. Yes, yeah. So 2 bonus points for the source panel problem. And there is a vortex panel methodology in chapter 4 as well, but we are going to cover that part if we had enough time at the end of the class, right? So we are not going to focus on that part. That's the first announcement. The second announcement is about next Wednesday. It is possible that I cancel the class on next Wednesday. If that was the case, I would send you an email on Wednesday morning, right? I will post an online lecture. So the class, I shouldn't say I will cancel the class. The class will move to an online version, full online version, if you will. So Wednesday class next Wednesday. So a week from today, maybe online. A pre-recorded online class, asynchronous. Is there any questions? Okay, let's start the class with a attendance quiz. We haven't had enough of these attendance quizzes, and they are part of the grade, so we're going to see more of them. Tell me, what do you think is the difference between flow over an airfoil and flow over a wing? What is the difference between these two? This is actually the topic of today's class. I just want to see how creative you are, if you will. And whoever gives the correct answer will get a bonus. Sure. Yes. Yeah, a generic airfoil. And the first thing you need to identify here is what is the difference between the flow over a generic airfoil and a generic wing. What is the main difference between the two? From there, I think we have mentioned this in class, but it has never been the topic of discussion. You have a question? You don't need to answer it. Just write down the answer on a note. If your answer is correct, you'll get a bonus point. And you need to submit your answers, of course, because this is, it will go towards your attendance check. You had an attendance check for the previous lecture, but that was just bonus. So whoever was here at the beginning of the class received the bonus. I haven't updated the bonus points yet, but can ask questions, you can talk to your peers and get their opinions on this. It is not a test, right? Just a quiz. Just want to warm up your minds. So I think you came in after we gave the question. The question is, what is the difference between the flow over an airfoil versus the flow over a wing, right? And I said the first thing you need to identify here is that the main difference between the two types of flow, right? That there is one main geometrical difference between the two types of flow. Okay, I think you have had enough time, so let's just submit your answers. I'll go over them, and whoever gets the right, thank you. We just pass your answers along, and whoever gets the correct answer will get bonus points. If not, thank you. Again, the point was to have an attendance quiz. I usually have the attendance quizzes at the end of the lecture, but I think it's a better idea to have that at the beginning of the lecture. That's an incentive for you to be present from the beginning. Okay, so we are going to come back to this question, and we'll go around. We'll go around the class and ask you to talk about your answer and your justifications for that answer. But first, we want to talk about different types of wings. So, as you can understand from this question, the attendance quiz question, the topic of today's discussion and the rest of the lecture is wings and aircraft, right? So we are going to move from airfoils to the flow over wings, right? To understand the flow over wings better, it is not a bad idea to learn about different types of wings. The most common type of wing that we have seen so far, we haven't seen, but the most common type of wing that in the analysis is the rectangular wing. And this is a top view. All of the views you're going to see here are going to be the top view of the wing. So if you look at it, this wing from the top, you will see a rectangle. Right? From the side, it will probably look like an airfoil, right? But from the top, it will only be a rectangle with a chord length that is constant throughout the wing, and a span, a wing span. Okay, that's the most fundamental type of the wing that you may use in aerodynamics or aerodynamic design. Then we move on to a more complicated type of wing, unswept trapezoidal wings, which we can understand from their names that they look like a trapezoid. Right? They should look like two trapezoids. This is their most general form. Again, this is a top view. And a span length again. Your chord length is going to change from your root to the tip. So this is actually another very good drawing, but this is how it's looks like. You're going to have a root chord and a tip chord. Let me ask you this question. So this type of wing, let's say this is a type of wing with dimensions that we actually produce and manufacture, right? What is the problem with this? That doesn't have the same dimensions, right? This is my mistake in drawing. My drawing we had to have same distance here, b over 2, b over 2. But since I'm drawing on the blackboard, this obviously is smaller than this. Let's say I give you this design, I tell you to manufacturers and build an airplane using this. What do you think you will see here? What will be the problem? So you're flying with a wing that is like this side of the wing is half of the other side, right? What will be the problem? You have more total lift on one side, right? So you constantly will have a moment in this direction, right? So stability is out of the picture here. There's no way you can fly this without any problem. So I guess it wasn't a bad discussion to have, but you just have to make sure that you understand that you have to have the same length from the roots. Okay. Two types of the wing. Another type is called the swept wings. Are called the swept wings. They usually have a sweep angle, lambda. They always have a swept wings, always have a sweep angle, lambda. And I think there's something I forgot to mention, that the quarter chord line is also a very important part of the wing design, quarter chord. Same as here, quarter chord line. And this angle for the swept wing, the quarter chord sweep angle may be different from the leading edge sweep angle. So we have the sweep angle at the quarter chord and also at the leading edge. The last type of wings that are very famous are called the delta wings, are a special type of swept wings. And quarter chord line will look something like this. This will be your Okay, so we start with a very simple type of wing, and then we increase the complexity to the quarter chord wing. The first half of this class, we will have a discussion about the different types of these wings, what are the different flight characteristics that are attributed to these different types of wings, and different parameters that are important here. Sweep angle in the swept wings is a very important parameter. It's actually a parameter that determines your flight performance, stability in general, and maneuverability. Maneuver, I think so, of the wing. It is a very important parameter in supersonic flights, and you will see swept angles in high-speed flight vehicles. What do you think will change when you introduce the sweep angle, or when you increase the sweep angle? Let's say you start from this wing with a sweep angle of 0, okay? Then you introduce a sweep angle. What do you think will change as far as the flight pattern goes? The flow pattern. I want ideas. What do you think will change? Yes. So a span is going to be smaller. Is that what you want to say? Okay. Yeah, that's one geometrical change. Yes, of course. Okay.
The less buildup pressure along the leading edge, because like when you're going through the flow, the air doesn't have to only be directed up or down; it can be directed more to, like, let's say, like the left or the right.
Okay, so what you're telling me is that you will see something like this, right? The flow movement, right?
Yeah.
Is that what you mean? Okay. Yeah, exactly. That's something that can happen on a surfing. Okay. And what would it mean, though? You don't need to answer that right away. Just think about it. So as Mohammed and Paul mentioned, like your span is going to change, your effective chord length is going to change. The chord length is in front of the flow pattern, and the flow pattern itself is going to change, which means that we will see a lot of changes when it comes to flight mechanics and flight performance in general. So introducing the sweep angle is very important, and you will see later on that the swept wings are mostly used in military aircrafts because of their specific designs. Okay, let's just define some parameters here that are very important in the analysis of wings. The first one is the wing area. I don't want to wipe it. So wing area, span area. That's B divided by C, the span area. That's the wing span divided by chord length. And this is true for a rectangular wing, right? Because the chord length doesn't change here. But what if we are dealing with a tapered wing, a trapezoidal wing? How can we calculate this span area? One way of looking at it is just we have to have the function of change function for the length of the chord and make it complicated. But the other way, which is usually the thing that is reported in the designs, is that they give you an average chord length, right? And then you calculate your span area based on that average chord length. And as long as you are consistent in your analysis, it will really affect your final bottom line of the analysis, of the design, right? Another parameter, another very important parameter is the aspect ratio of the wing. Let me write it here. How can we find the aspect ratio of a rectangular wing? Or do we understand? Let me ask you this first. Do we understand what aspect ratio is? B divided by D, exactly. So aspect ratio is actually the ratio between the span length and the chord length. And this is true for everything. Aspect ratio of anything is width divided by, this distance divided by this distance, whatever you want to call it. Width, depth, length, whatever you want to call it. Okay. But how can we calculate this aspect ratio if we were not dealing with a rectangular wing? We can simply use the area and the span length, wing span, to calculate the aspect ratio for the delta wings, for the swept wings, and for the tapered wings or trapezoidal wings. What is the significance of aspect ratio, though? Or let me back a little bit. Let's take a look at this. What would be the difference between two wings? One has an aspect ratio of 1, the other has an aspect ratio of 20. And when it comes to how they look, the top view of, what would be the difference?
One of them, which has aspect ratio of 2, is twice longer.
So that we had 1 and 20, right?
Yeah, the chord is 1.
The one that has the aspect ratio of 1 is going to look like a square, right? B is going to be equal to C from the top view, right? A square, right? The one that has aspect ratio of 20 is going to look like this, right? Aspect ratio. But the question is, why is this important? Why is the aspect ratio important? This is something that I want you to think about.
I think it makes sense, like visually, like it has like a certain to the length. Like I think you just have to have say like aspect ratio like 3 or 4 or something. Like, if not, then maybe it would have
Generate enough lift. So what you're telling me is that this does not generate enough lift, right? But it has a very large area though, right? So you are leaving enough room for air on the bottom to push the wing up.
like since the height is too like long, would it cause like more drag? Because it has to like stare and flow over the surface for longer.
So we have one answer that the aspect ratio, actually, higher aspect ratio wings are going to have less drag. Okay, that's a good approximation, right? Not necessarily true in every case, but on a rectangular wing, yeah, that's true. What else? What else do you think? That's actually on this, and yes.
It usually affects the area that is engaged with the moving air, can this area affect the result of drag coefficient and lift coefficient both?
What? So can I design a wing that has the same area but different aspect ratio? Right? Area will be the same. So what would be the difference between the two wings then? And let's say these two have the same area, right? Let's say this has, I don't know, 4 by 10, no, 4 by 4, 16 meters by 1, right? Aspect ratio of 16, aspect ratio of 1, same area, right? What would be the difference here? So you have the same amount of air, right? Joshua, right? Joshua's argument may be true in some cases, that Why can't it? Okay. It should be, yeah. Why did it turn on? I'm sorry. I don't know how long they couldn't hear me, but I just saw this comment. Go ahead, please.
So the reason you're focusing heavily in you have broken the velocity components of the system is that means that the lift potential is generated in the forward flow and not in the standby flow. If you use the standby flow direction, your actual value will be lesser at calculated values and will introduce more drag.
Okay, so what Muhammad is telling us is that we are going to have lower lift and higher total drag. But I didn't understand what was the reasoning behind it. Let's see. Do you guys can hear me on YouTube, on Blackboard or YouTube or whatever? Let's just see what is going on here. SMS answer over email. I think so. I don't know if there's anyone still here. I'm sorry, guys. Yes. Okay, that's good. And you can also tell me how long you couldn't hear me. But yeah, what was the reason? But what does a z direction flow do? Why? Okay.
You need some way of controlling or else you are going to lose control of your car.
Okay. But what is that yaw effect in the level flight? That is important. What happens to the flow? Like in the yaw direction, right? Or it is in the wrong direction, but what happens to? Okay. There's no way for me to fix this in this case. Let's actually go to turn on.
what happens if we move into three-dimensional society?
Okay. Wingtip vortices. Wingtip vortices. Yeah, so what happens with the wingtip vortices? I don't think they hear me. Let me just tell them to go to Blackboard. Go to Blackboard. Leo. Yeah, what happens with the wingtip vortices? Okay, so yeah, exactly. So is there anyone else who wants to jump in and talk? Actually moved a little slower than I expected. Well, let's talk about this and then we can continue the discussion in the next class and everyone can hear me. Hopefully to make sure everyone can hear. So let's have a front view of your of our wing, right? What is going to happen when you have a wing compared to the two-dimensional airport? A front view of a two-dimensional airport is essentially an infinite wing, right? So there's nothing happening in this direction. But when you have flow going here, we have a high pressure, high relative pressure on the bottom and low pressure on the top. When you have a high pressure region and a low pressure region that this high pressure region can have access to, what is going to happen? The flow is going to go from bottom to the top, right? So you are going to have flow leaking from the bottom surface to the top surface. Okay. What does this mean? This means that you will lose some of the pressure difference. So pressure, specifically at the tip, is going to become the same on the top and the bottom, and the pressure difference in general is going to reduce a little bit, right? So for a two-dimensional case like this, the distribution of lift on the wing, very thick wing, that's right, is going to be linear, right? Because the pressure difference is going to stay the same all over. And this is an infinite wing, right? But on a real wing, on a three-dimensional wing, since the pressure difference here is zero, your lift at the tip is going to be zero, right? So you will see the highest lift at the middle or on top of the fuselage, then it will go back down to zero, right? It's because of this flow leaking from bottom to the top. You will have zero pressure difference on the tip, a smaller pressure difference near the tip, and your pressure difference or effects of this leak is going to vanish when you get to, or is going to be less dominant when you get to the fuselage or the middle of the wing, right? This phenomenon is called the downwash. And because of the movement of this flow, because of this flow pattern, what you're going to see when your aircraft is moving is that this part is going to leave the aircraft like vortices, right? That's what you see wingtip, what that is, as Terval mentioned, what we call wingtip vortices, right? So wingtip vortices are there because of the downwash phenomenon. And the goal in chapter 5 is going to calculate the distribution of lift and also we are going to talk about drag as well in this case. Okay, so let's stop here. I'm sorry, online people, that you lost audio. I guess I should have charged this before the class. It ran out of charge. And it is raining outside, so be careful. And again, next Wednesday we may not have an in-person class, but I will send out an email, right? If you did, I will definitely send you an email anyways. Okay. Have a good weekend, I guess.